So now let's put our 18 electron rule and our ligand examples for how to determine how many electrons are coming from each species and do some examples for electron counts. Now, keep in mind that even though I mentioned the 18 electron rule, it's possible that some of these do not have 18 electrons, and so we should actually count them. So we have ferrocene, which is an iron with 2 cyclopentadiene ligands on it. So if we want to draw this, this is kind of a neat compound. It's a sandwich compound. So it's an iron that's sandwiched between 2 ferrocenes. And some people have actually used this as a ligand, so they'll put some phosphorus atoms coming off of here, and then they can have ferrocene actually be part of a ligand. So you can have an organometallic complex be a ligand for another organometallic complex. Not to get too meta on us, but that is kind of a neat thing that you can do. All right, so sidetrack over, let's talk about electron counting in the ionic model. Now we have 2 CP ligands. Now, in the ionic model, we consider that the additional electron goes to the cyclopentadiene. So we have 2 L ligands for each cyclopentadiene, and we have an X ligand. And then the ionic model, this CP has 6 electrons each, right? Because X ligands count as 2, L ligands always count as 2, so we have 2 L's, 1 X, that's 6. And now we have 2 CPs, so that's really 12 overall. So hopefully that wasn't too confusing. And then, since we're talking about the ionic model, we need to consider that since these ligands are negative, our metal is now positively charged. This is a -1, that's a -1, so our iron is Fe2+. Now, iron 2+, if we count the number of electrons, valence electrons that it has, that is 6. As it's a D6 and it's lost all of its S electrons. So that is 18 electrons. Now we should be able to count this in the covalent model and still get 18 electrons. So let's see what happens. 2 CP ligands plus, now in a covalent model, we're not going to consider the iron to be charged. So this is iron 0. And so now our CP ligands are 2 L's, which each contribute 2 electrons, so that's 4. And then we have an X ligand, and in the covalent model, an X ligand gives 1 electron, so that's 5. So each CP gives 5 electrons, there's 2 CPs, so that's 10. And the iron is D6, but since it's 0, it also has its S electrons still there. So there's 8 total, 2S, 6D. And imagine that we get 18 electrons. And this is an important point. Both the ionic way of counting electrons and the covalent way will give you the same result. It really comes down to which one do you like best, which one do you find most convenient, pick it and go with it. It's not really important which is which. Sometimes it could be convenient to use the covalent model because if you have a lot of, if you have more than one metal in your complex, it can be difficult to assign an oxidation state to the metals and know which is which. So using a covalent model can alleviate that problem, but it doesn't come up too often. All right, so let's now move down to this one, which is a molybdenum with some hydrides and some phosphine ligands on there. Now you may notice that there's quite a few ligands on this atom, but quite a few of them are hydrogen, and hydrogen is small, so you can usually fit a few more on there if you want. So here's 4 hydrides, and in the ionic model, let's see here, this is going to be 8 because it's got 2 electrons to make it negatively charged. And then we have 4 phosphine, and this will also be 8 electrons because these are L ligands, so neutral. And then since this is ionic and those are H negatives, this must be molybdenum 4 plus. So there's 2 electrons for that. And then if we add that up, we should get actually 18. Now we can do the same thing with the covalent model. Now in this case we'll have hydrogen, we'll have our 4 phosphines, and we'll have our molybdenum, which is now in its 0 oxidation state. So this will have 6 electrons. It's got 2 s and 4 d electrons. This one has 8 still, because neutral ligands have the same number of electrons no matter which model you're counting. And now the hydrogens would only have 4 because they're neutral now, and hydrogen only comes with 1 electron then. Add those up, still 18 electrons. Now I know I said that not everything has 18 electrons, so let's do a case where we might not be 18. So we have a nickel with 2 allyl ligands on it. So we have our allyls in A to 3 because it's bound to the 3 carbons here. And in an ionic model, this is an LX ligand, if you recall. So ionic, that means there's 8 electrons here. And then we have nickel 2 plus because this is a negatively charged ligand, which is D8. So 8 electrons. We total that up, that's 16 electrons. Now we can come over here and count it the covalent way. So we have 2 of these. I'm just adding an electron there to kind of note that this was a negatively charged ligand. So there's 2 electrons here and 1 there. So, and then 2 of these ligands. So that's 6, right? Because there's 3 in each one. And then we have nickel 0. So that is 10 electrons. So we get to 16. It should be 16, assuming we did the other one correct. Now, like I said, not every complex has 18 electrons. And in fact, we can see the electron count change during a catalyst cycle or during a reaction. But keep in mind that with very few exceptions for the transition metals, the electron counts stay below 18, 18 or below. This is just typical. Now, if we were to move over into the lanthanides and actinides, of course, we would start involving f orbitals, and then there would be a lot more availability for electrons, and the electron counts can get a lot larger. But in this class, we're focusing on the transition metal elements, those generally follow the 18 electron rule. It can be the case where you can get a 14 electron complex as well. Those are quite common, and it's fairly common that during a reaction cycle or catalyst cycle that the electron count would alternate between 14 and 16 electrons or 16 and 18 electrons. One of the things to pay attention to is that when we're writing a catalyst cycle or when we're trying to propose a mechanism, it's a good idea to make sure that you don't go beyond 18 electrons in your structure. That would be a bit like having carbon have 5 bonds. That is something that's not really allowed, and in the case of a transition metal complex, you're probably not correct if you go above 18 electrons. Again, there are a couple of exceptions, but most of the time those would not come up, and they're unstable anyway. So it's unlikely that that would be part of a catalyst cycle, for example.